It's a pleasure to talk today. So let me first thank Antoine, Olivier, and Thomas for the kind invitation. Let me also acknowledge my collaborators. Actually, this project started 10 years ago with my colleague Isaac Snyman from Johannesburg, where we understood that bosonic impurity problems actually were kind of simple. And since we knew there was a connection between bosons and fermions, we tried to translate this knowledge into fermionic models. It took us a bit of time, and we developed methodology, which I will not go into detail today, but one major problem was that this methodology relied on some kind of variational, optimization, and optimization is a nasty beast. So then entered Maxime de Bertolis. He was a student in my group, but also supervised with Isaac. And Maxime really pushed these ideas and really made them systematic, controlled in a very intuitive way, basically building on the natural orbitals. So I will present part of the work Maxime did at the beginning. And in the past 2 years, we've been joined by a bright postdoc, Uriel Nunes Fernandez, who brought new ideas, especially tensor network techniques, that allowed us to merge both ideas, natural orbitals, and basically matrix product states. And this will be the main topic of the talk. Okay, so let me start with a very quick motivation. I'm not sure I need this for this audience, but okay. So if you're interested, let's say in DMFT approaches to strongly correlated systems, you need a very good quantum impurity solver. I guess you all know that. And this is typically the Father Christmas list of what is required to make life good. You need some algorithm that has controllable errors, that is very fast, if possible, and efficient. That provides observable, if possible, in real time and real frequency. Although imaginary time has some advantage, but at the end of the day, this is what we measure. The question of the bass is also very important. I will show you some example. In principle, you would like to describe microscopic bass. If possible, the algorithm has to be multi-orbital friendly, which is still a challenge today. It should be able to handle bosons and fermions equally. And there are a lot of very interesting physical questions about non-equilibrium physics, like transport, quenches. And so this algorithm should also be able to tackle these regimes. Okay. Of course, quantum impurities are not just a nice mathematical device. They're also physical things. And of course, this starts from 100 years ago with first experiments on what we call now Kondo impurities in metals. And let me flash actually what is, to my view, like the front of research in recent years. So one big advance we've had in the last 10 years is that now we are simulators of bosonic impurity models. These systems built on the technology developed for building quantum computers. So in this case, superconducting circuits. So this is one example. This is an electron micrograph picture of a device, which is made of a superconducting qubit that you can take as a quantum impurity, two-state system that is coupled to a very controlled environment. In this case, this is a system made of 4,000 microwave resonators, which is a bus of bosons, which we can resolve, so we can monitor the dispersion relation of this environment very precisely. So in this peculiar device, this is a realization of the spin boson Hamiltonian, but one is just limited by imagination, I would say. And these systems provide a lot of interesting physics and theoretical challenges. This is not the topic of the talk, but you can refer to the work by these two people if you are more interested. Okay, another, I think, new development is, so now on the fermionic side, is time control. So in the last really few years, people have started to probe electronic devices in the interesting temporal range, which is typically the terahertz or the picosecond range. They use a variety of experimental techniques that I will not detail here, but they are able to propagate wave packets on very short time scales and make this wave packet interact with various kinds of nanostructures like quantum dots and measure the response in real time. And I think this is very exciting development for the future. Okay. One question, do you see my mouse pointer?
Yes.
Yes, okay.
Yes, absolutely.
Okay. So the main idea of the talk will be kind of very theoretical, but it will be simple. And the main idea is that quantum impurity problems actually are few body problems, but not many body. So let me start with some simple introduction, just with a band of non-interacting fermions with a local one-body potential. So this is a solvable problem for systems that are not too large. And we know that the wave function of this full Hamiltonian has orthogonality catastrophe, namely it's orthogonal to the ground state without the potential. But it's not so bad because the ground state of the system is still a Slater determinant, okay, which you can rationalize by the eigenvalues of the one-body density matrix. Okay, so you compute this expectation value in the state, and the eigenvalues of this object for a Slater are just 0 and 1. You can see it obviously by going to the eigenorbitals of this Hamiltonian that I did not see A. Psi is just a product of CAs with occupation 0 and 1, and there you go. Okay. One important thing to note is that degenerate orbitals with respect to the occupations can be rotated freely in a Slater, and this I will use later. Okay, this is due to Pauli principle. Okay, so what happens if you put interactions? So if you have bulk interactions on a lattice, like the Hubbard model, this is pretty nasty. So you start without interaction with a free, the distribution function of a free electron gas, and you move to something like this. This has a finite jump at the Fermi level, and then some dispersion of the occupations. So the occupations are, of course, the momentum distribution function due to symmetries. And these numbers are typically different from 0 and 1 always. And even if you are far away from the Fermi level, these numbers go to finite values in general. Okay, so moving to this basis will not save the day. Now, if you move to impurity models, although the problem on paper in the Hilbert space is many-body, the core physical ingredient is that a local interaction, so impurity models have interaction that act just on a few sites. And so it's acting on a macroscopic state, which is this huge Fermi, Slater determinant. And so this small perturbation cannot really mess up the whole Fermi all the way. And as a result, the occupations that you obtain from the density matrix are never very different from 0 and 1. Okay, I will show you some examples. And the goal is to reveal the structure and use it to our benefit. Okay, so in this second part, I will focus just on ground states of impurity models. Okay. So the use of nature orbitals is, of course, not new. It's a very old idea that date back from the 50s. It's a crucial ingredient in modern codes of quantum chemistry. There are very important ingredients to optimize the code, but to my understanding, I think you get more bang for your buck if you move to quantum impurity models, meaning this orbital rotation offers a lot of simplifications. Okay, so I already mentioned that a state that looks many-body will become few-body, even if the system is macroscopic. As we will see, entanglement will be strongly reduced, which is very important. Also, a big advantage is that, obviously, if you do orbital rotation and you have interactions everywhere, the interaction which is local will become a mess. It will be a 4-index tensor. It will be a very complicated object to encode. Impurity models are very specific in the sense that you can perform, and you should perform orbital rotation without touching you, meaning without touching the interaction. So you rotate essentially orbitals in the bus. Okay, and this is very important for a numerical perspective. Okay, so I've listed a couple of important references in the past few years in case you're interested in various ideas. Okay, so I will focus in most of the talk in an Hamiltonian that you may not be very familiar, which is called the interacting resonant level model. It's a model that is nice for developing code because it's pinless fermions, so you have one less thing to think about. But this model encodes all the nasty physics of Kondo impurities. Okay, so let me go through very quickly the main ingredients. So this model is a chain of fermions. Site 0 will be the impurity. This site is coupled via hybridization V to site 1, so this term here, and also via Coulomb interaction. Okay, and the first site of the chain is coupled to the rest of the chain by uniform hoppings, the D2, so this leads to bandwidths or half bandwidths of D. Okay, so you have a chain, hybridization, and interaction. Okay, so this model looks a bit trivial. Actually, you can map it exactly to an anesotropic Kondo model, where the local charge on this impurity is basically the spin of the Z polarization of the spin of the Kondo model. This hopping is basically the usual exchange term, and so on and so forth. Okay, what is a bit counterintuitive is that the strongly correlated regimes of this model, meaning a small renormalized scale, so very small TK compared to the hybridization of the impurity, happens for negative interaction. Okay, this has to do with lifting of the degeneracy of this quantum impurity. So the nasty regimes are for, or the complicated regimes are for negative U. For positive U, the dynamics is, or the thermodynamics of the problem is much simpler. Okay. So let me flash a few results that were obtained during the PhD of Maxime de Bertolis. What I'm plotting here are the natural orbital occupations. So they are called lambda n in this slide. This is what I used to call NA in the previous slides. So these are plotted, these are extracted from numerical RG calculations, which rely on the discretization of the band on the Wilson chain, so typically on scales that go down exponentially fast as you progress along the chain. So you can reach really small, exponentially small scales with this method. And what is plotted here is nothing but a plot like this one, which I have folded. Okay, so this one you're familiar with. This plot, what I'm plotting is either the occupations that are smaller than 1/2, or 1 minus the occupations that are bigger than 1/2. And as a result, I can plot all these things in log-log. Okay? And since the model was taken to be at particle symmetry, the plot is symmetric. Okay. So, this is the vertical axis. These are these occupations. The horizontal axis is just ranking the orbitals according to their occupation from the most active ones. So occupations that are closest to 1/2 to the most inactive ones. So either occupations close to 0 or close to 1. Okay. So what you see here in this plot is a very fast decay of these occupations. The decay is actually exponential. The rate of decay depends crucially on the strength of interaction. And if you recall the fact that the strongly correlated regimes are for negative U, this is not surprising that the rate is actually decreasing. Okay, the problem should be harder if you have a very small Kondo temperature. You will mix up a lot of scales, and this is what this plot is showing. For positive U, the rate is very fast. Okay, so not many orbitals are very important. For very small TK, you need to take into account more orbitals. Okay, So this is for this spinless model. We get basically the same picture for the spinful Anderson impurity model, except the extra spin degeneracy. All right. So one word of caution about analyzing orbital occupations is finite size effects. Okay. So let me show you one example. This is still on the Wilson chain, and this is a run where we have driven the Kondo temperature to be crazy small, like 10 to the minus 10. Okay. And what you see in this plot, so this is the same plot as before, just the right quadrant. So occupations of the orbitals as a function of orbital ranking. And this is done for various system sizes. Okay. And so you see, for the highest orbitals, the convergence looks good. But as you go down to small occupations, you see a lot of finite size effects. Okay. So as you increase the system, it will converge. Fine. And so what I'm going to show you is basically this set of orbitals, as you see here. So I'm extracting 5 orbitals, and I plot versus system size. Okay. Remember, this is a Wilson chain. So when n is 100, this is a crazy system with billions of sites in real space. Okay. And so what you see here is that for short systems, the system looks like a really weakly correlated problem where mainly one orbital is active and all the rest are inactive. Okay, and so if you were to cut your simulation here, you will conclude that the problem is relatively simple. What happens is that the problem has a natural length scale or energy scale, the Kondo temperature or the Kondo length. And to develop fully the correlations, you need the systems to be larger than this typical length scale, or equivalently need to be able to reach smaller energy scales than the Kondo temperature. And once you hit this scale, which is about here, some orbitals start to be active. Okay. So this is a word of caution to say that to fully develop the Kondo correlation, especially when the Kondo temperature at the end of the day is very small, the bass must be large enough to accommodate the Kondo length. If not, you will cut the Kondo cloud and preempt the correlations. Okay, the simulation will look converge, maybe in the many-body way, but not regarding the thermodynamic limit. Okay. So about this part, so this study is basically based on numerical RG. Of course, the orbitals are extracted from the many-body calculation, so we are not taking any advantage of this structure. We are just witnessing some simplification. And so the question that Maxime solved was how to take this into our advantage. So the idea is clear. If you go back to this plot, if you allow a certain level of accuracy, let's say about here, all these orbitals that are either close to empty or close to full, we will just exactly freeze into strictly empty or full orbitals. Namely, we will take them in a perfect Slater determinant. Okay. So this leads to an ansatz, which is very simple, which we call the few body ansatz. This is based on all the fermions in the problem, but we split into 2 types of fermions. Fermions from 1 to m are active, meaning we exploit all the possible Slater determinants, all possible configurations, and all the other fermions, n minus m orbitals, are in a perfect Slater determinant. Okay. So there are various ways to benefit this structure. Let me briefly mention one. We developed in the work of Maxime a way to construct these wave functions in a recursive manner. The basic idea is to bring states into the game one by one, do an exact diagonalization of this few body problem, compute the one body density matrix of this reduced system, and in order to update the orbitals, and then throw away the orbitals that are less active, that are the least occupied, or least, closest to full occupation or closest to zero occupation. And then we do this repeatedly by sweeping the whole system. And at the end of this process, we have built this state in a very systematic and controlled way. Okay, so this is an example. This is a calculation done again on the Wilson chain, where we compare the ground state energy from this few body ansatz to the numerically almost exact energy computed by numerical remuneration group. Okay, so this is the energy difference as a function of the number of orbitals in the active sector, so the number of fermions in this part of the wave function. And as you can see, as m increases mildly, this energy converges exponentially fast to the actual value. Okay. As expected, the rate of convergence will depend on the correlations. If you remember, negative U is strong correlations, and of course, the energy will converge more slowly. Okay. So why is this interesting? We have numerical energy to compute many things. One thing that this technique allows you to do is to perform calculations on quantum impurities on real space lattices, tight binding models, with possibly very large system sizes. So we've done computations up to 10,000 sites. So this is one example of some observables, which is a Kondo cloud observable. This is a charge correlation function between the impurity site and a site at distance I, which has some non-scaling that I will not discuss in detail. And this was one of the first calculations that were done with such large systems. Okay, these calculations can be done with numerical energy, but are really tricky. This is single-shot calculation. We build this whole function, and this observable is computed for free. This technique also allowed us to do things that were, to my knowledge, very hard to do, which was to do statistics of disordered impurity models. This is one example of an Anderson impurity with charge disorder, where we computed the distribution function of the Kondo temperature. It has a very rich tri-model distribution. This is understood in terms of the physics of the model. And to get this kind of statistics, you need a very fast impurity solver because these are thousands of runs, typically. Okay.
So Serge, I just want to understand the model with disorder that you have. So these are a number of realization of the same Anderson model with different value of the charge interaction, or this is on the lattice with some disorder, or what's the model?
Yeah, this was Anderson disorder model, so this is real space disorder with
in the chain.
In the chain with local potentials, yes.
Okay, thank you.
Okay, so let me now move to a more modern implementation of these ideas. This has been pointed out previously, that the way you implement the bath, the geometry will crucially determine the quality of the ansatz. This was actually discovered quite lately on impurity models, that actually the star basis, so the k-space basis, was actually more effective than the real space basis. And the reason is that in real space, orbitals are kind of half-filled, so they're all active, while in k-space, the orbitals that are far from the Fermi level are mostly inactive. Okay, so this is what you see here. These are MPS computations. In real space, all the k's for all orbitals are pretty large. For k-space, which is called the star basis, you go to a maximum and then some kind of slow decay. Once you move to natural orbitals, so this is a recent work that we put online, the decay is very fast. The values are very small. And as you see here, k equals 1 means you get a perfect Slater determinant up to the precision or the threshold of the calculation, which is the few body picture. Okay. So of course, for ground states, we have a lot of algorithms. So why and how can we make this very more useful? And I think the best case is dynamics. Of course, dynamics is a much harder problem. So I will focus on a simple protocol. I'll take the same spinless model as before, and I will quench the local charge on the impurity in a way that at time t equals 0, I have 1 fermion on site 0, 0 fermion on site 1, and then a Slater Fermi C in K-space for the rest of the chain. Okay, so that's my initial state. And if I do a real-time evolution of this state using the MRG, the usual one, it will start by a pretty expensive state because the DMRG is in real space for this calculation. And then the bound dimension will increase very fast as a function of time, and you have to stop the simulation very quickly. So the question is how to use orbital rotation to simplify these dynamics. Okay. So there are two ingredients that we want to exploit: few bodiness and low entanglement if possible. Okay, so the use of orbital rotation in MPS has been tried, but not to a big extent. So there are a couple of papers. There are lots of general problems. If you have models with interaction in the bulk, this is nasty. You have interaction everywhere. This is very bad. You have problems of continuity. The dynamics could lead to jumps due to degeneracies or ordering. This is bad for some time-dependent protocols. And the main issue is that actually rotating a state, and especially an MPS, is very expensive. Okay, so these are general problems. And the key point is that quantum impurities alleviate most of these problems after you make a couple of tricks. So the first problem, which is orbital rotation of the interaction, this is easy because we just don't rotate the orbitals that are interacting together. So the one that are coupled via the interaction U are not rotated. Okay. The key question about entanglement relies on a couple of tricks. So the main idea is to never, or as little as possible, perform a rotation of the NPS, which leads us to an ansatz of this form. So this is the many-body wave function at the time t. And what we do is to use an arbitrary frame that I call f, which is just a rotation matrix, exponential of f, with a bilinear of fermions. Okay, and this operation is never applied to the state. This operator will be applied to observables, but not to the MPS. Okay, and the simulation will be done within this state vector. Okay, to make the computation feasible, you need to use a few-body structure, and this is done by revealing the structure from the one-body density matrix. So at the end of this procedure, the state, so this state will be a low-rank MPS with few active orbitals times the Slater determinant. Okay. If possible, orbital rotation has to be made cheap, and we use typically quantum circuits, okay, which also use the impurity structure. So how this is done? So there are various ways to do the evolution. The simplest is to use a trotter decomposition in this form. We separate the impurity, which are sites 0 and 1, so interaction, hybridization, and the first hopping to the chain, with the rest of the chain. Okay. If you do that, you use a trotter dynamics at a short time dt. So the evolution operator is this one. This is exact. And then you approximate by decoupling these two terms. To be clear, there is a second order correction due to Baker-Campbell, which I didn't write, which is important to get good accuracy. Okay. So now you see one illustration of the idea of using a frame is that this part, which is macroscopic and which is responsible of most of the entanglement, you put it back into the frame, into this thing that you don't apply to the wave function. And you do this at every time step. Okay. So most of the complexity has been removed using this idea. Okay, so the second simplification is to exploit the few body structure. So at a given time, you can compute the occupancies of the natural orbitals, the diagonal the one body density matrix, and you can rank them by activity. So you have the active orbitals that are between epsilon and 1 minus epsilon with a very small threshold. You have the empty orbitals that are smaller than epsilon for the occupations, and the full orbitals that are close to 1. Okay. The approximation will be to freeze exactly again these empty and full orbitals and put them strictly in a Slater determinant. Okay, so what is very important is that the trotter dynamics now is only the impurity term, which is this term. It's basically internal to the impurity and has only hybridization to one side. Okay, so the key term will be the hybridization, which is this hopping term, which you can express in the basis of the new orbitals. So C2 is the side 2 of the chain. You can express it in the current basis of your environment, CA. Okay, but it's a linear operator, so I can decompose this set of fermion operator. There are as many as the number of sites into 3 fermionic fields. One placed in the active sector, it's a projection, one in the empty sector, and one in the full sector. And what you see right away is that this term becomes only active in an expanded space, which contains the M active orbital plus 2 extra orbitals, which are the empty and the full orbitals decomposing this interaction or this hybridization. And so the key point is that after you realize that, is that all the remaining n minus m plus 2 orbitals, they remain empty and full, and they stay in oscillator. So the time evolution will not touch the oscillator up to activating 2 orbitals only. Okay, so now you can evolve the MPS by numerical means. And if you do nothing, you still have a problem, because the active space will increase by 2 units at every time step, because you bring 2 new orbitals. And you will see also that entanglement will grow in time. Okay, so the idea is to recompress the state at every time step. And for this, we use an algorithm that was developed by Fishman and White, which is to use a shallow quantum circuit on the eigenvectors of the density matrix in the active space. Okay, this has 2 benefits. When you extract the smallest eigenvalue of rho, typically what you will see is that it will define new orbitals and new occupancies, and most of the time these occupancies will be below the threshold, meaning you can throw them again, and meaning you're back to m orbital again. This is what I'm showing here. The number of active orbitals versus time is of course increasing, but it's not increasing linearly. It's increasing by steps, but after a while you see formation of plateau, okay? And at some point it just saturates. At this time, the evolution becomes very simple. Okay, so this using this compression. What I'm not showing is that when you repeat this process for all orbitals, you redefine the occupations, but also you decrease the entanglement, okay, at every time step. And this is a result of this process. So this is the maximum bond dimension of the state, this free body state. This is again for real space orbital, and this is for the time-dependent orbital. You see that it grows very slowly and saturates at long term. Okay. So the key result is that using this algorithm, we have a state that is few body and low entangled even at very long time. I'm not sure how I'm going with the time.
Well, if you want to keep some time for questions, you should try to conclude in a couple of minutes.
Okay. So to conclude quickly, let me tell you that we have benchmarked this algorithm very carefully. Also, we have benchmarked the trotter errors and so on various solvable cases. We have been able to push the quality of the MRG simulations that were previously limited to, let's say, 1% of error down to 6 digits of errors, while speeding up the calculations by order of magnitudes. So this kind of calculation can take between minutes to hours, depending on the accuracy you want. So it's like having the cake and eat it. It's faster and more accurate. This method allows us also to explore very nice physics. So very quickly, this is a snapshot of the charge emitting in the shade. So the impurity is located here. These are different time frames. So what you see is the emission of a charge wave packet at different times. And at the same time, a decay of the Kondo correlations, which is expected because at long distances, the entanglement between the impurity and the environment goes down. Okay, let me illustrate it by a pretty nice movie. So this is the emitted charges and the Kondo correlations as a function of distance and for different times. You see the emission of a wave packet. And what is very nice to see is that, sorry, let me do it again. Here, at a given time, it's a long time where the wave packet is away from the impurity. All the correlations that are formed, okay, saturate to the expected ground state correlation that are computed independently from a DMRG calculation. And this is expected because the system has to relax to the ground state. It's a dissipative process. So all the Kondo correlations have to build along the time. And this is what we see here. So the blue points align with the ground state points. Okay. And at the same time, the bond dimension which is shown here doesn't grow and saturate. Okay. So this is the main conclusion. We have managed to use orbital rotation in the framework of matrix product states to improve the computations of dynamics of quantum impurity models. This dynamics is few body and has low entanglement, which allows us to do simulations up to very long times and high accuracy. There are lots of things we want to do. Obviously, extend the calculation to Green's function, multi-orbital impurity models, and also try to tackle transport geometries like DC and AC transport. There are still a lot of challenges. I don't think this is the end to impurity solver. There are lots of problems that are still hard, I think, even within this method, like protocols such as periodic driving, or some kind of bosonic models which has a lot of quantum fluctuations, meaning truncation of the bosonic space can become an issue. I think we still need new ideas to tackle these problems. And with this, I want to thank you for your attention.
Thank you very much, Serge. So the talk is now open for a few minutes discussions.
Yeah, hi, Serge. Thanks for this very intriguing and inspiring talk. I was wondering, could you say a few words about the challenges involved in computing equilibrium Green's functions? Because when I saw your preprint, I was wondering, well, what about dynamics? It's sort of the natural next step.
Yes. So one way to go is to use a quench. So meaning you will excite one quasi-particle onto the ground state of the problem, which is written as an MPS. Let this evolve and then reproject on the same state. Okay, that's a way we could use the current algorithm to compute Green's function, right? Mm-hmm. We have done computations that seem to show that the structure, I mean, it's a different type of quench. It is simpler in the sense that we start with something that is close to the ground state. We seem to find that the same picture remains. Okay, it doesn't become more nasty. Okay, one case where it becomes nasty, maybe I can show you. I don't know if you see my other screen.
Yes.
One nasty case is if you start to bounce the quench. So this is a long-term simulation where we let the wave packet come back at the impurity. What you have at this time is a Kondo state, which is few body, but okay, and a wave packet which is also few body-like. It's not just plain waves later determined. This wave packet contains correlations, and so you get some kind of many body scattering process. If you monitor the bond dimension, you see at this stage it's small, it's 10. When they collide, boom, the state becomes much more complicated. I think this is expected because it's a more complex quench where we scatter many few body state into a Kondo state. Okay, So this type of dynamics, and we can follow it to long times. We can do times that are crazy, like 10 to the 4 time scale. But we can follow these dynamics to very long times as well. Okay. Yeah.
Okay, thank you.
Thank you. Andreas?
Hi, thanks for your talk. As a follow-up question, so when you do the time evolution, you're doing trotterization.
Yes.
And so to what extent are you limited by trotter time step? So can you increase kind of the trotter time step by some extent, or what's the limitation there in terms of how long in time you really can go?
Yes. So right now the algorithm is so fast that we can really reach long times. We are not limited by that. But of course, if you think DMFT, you want to have very fast impurity solver. And the question is whether you can make some kind of adaptative time step in the trotter. I think that would be very nice. So one has to be careful of where are the trotter errors, and whether we can push some trotter errors to either to higher order. That will be one way to go, or to use larger time steps when we can. And I think a regime where we can reach large time steps are typically long time, because at long time, the trotter error is basically local to the impurity, because we decouple locally. But at long times, what happens at the impurity is nothing is happening there because it has relaxed to the ground state. So my guess is that we can speed up calculations really in the long time limit. But I think we need a few tricks to do that. The code is not ready to that.
Different question still. So this was all on the non-entangling resonant level model?
So the dynamics, yes, the ground state was done for Anderson impurities as well.
For that?
The Anderson impurity model was studied only for the ground state.
Okay.
And we have not performed dynamics there, but I'm sure the structure will remain because all the nasty correlations are in this model. The Kondo correlations are there. So I don't think Anderson will be harder than what we've done, if that's the question.
Yes, it would be good to see.
Yes, of course.
All right, thanks.
Okay, Jeremy?
Hello, can you hear me?
Yes.
You just said that you are using the natural orbital and you're solving the impurity model in MPS. And I have a question: how many impurity orbital can you use currently in your program? Yeah.
By impurity orbital, you mean active orbitals?
No, what I mean was impurity orbital, which the orbital has interaction.
Okay. So right now, this code was only tested for 2 orbitals in the impurity. If you have spinful impurities or more complicated orbital degeneracy, you have to design the algorithm to take advantage of some structure. So this is what we plan to do, but I cannot say what will be the quality of the algorithm in the multi-orbital case. I think if you have SUN symmetry, which is a bit artificial, I think we can make a lot of progress.
Okay, so I have another question. Can I go on?
Yeah.
Yeah. So in 2 orbitals, how many bars do you use? And what if you are try to improve your impurity orbital? So what if you try to improve? What can I say? What if you in adding the number of impurity orbital? So you can the maximum of the imperative orbital can you calculate? So I have 2 questions.
I'm not sure I understood. So regarding the base degree of freedom, there's always a way that you can always make linear combination of the. So the key thing is number of active channels, not really the bus. Okay. For this model, it's only one active channel. Let's see, if you go the route of multi-orbital, this will be, so it will just not be one orbital here, but maybe several. So you will have a matrix, not a vector. The question is how many active channels you have. Typically, you have at most the same number of active channels as the number of orbitals. And so the scaling will still be linear, I would say, in terms of the number of fermions that you need to take into account.
Okay. So
okay.
okay.
For further question, I suggest that you communicate. We're a little bit behind. We have time for one quick question, maybe Antoine, you wanna?
Yeah, very quickly, but we can discuss more, Serge. Could you do mixed fermion boson problem, like, for example, effectively introducing screening channels to represent a time-dependent, frequency-dependent U with retardation?
Good question. So we have lots of experience on bosonic models. The same simplification occurs there for the same reason that interaction doesn't mess up a macroscopic state, whether it's fermionic or bosonic. The only nasty case is really if your bosons is strongly fluctuating, you have to be careful with the boson trocation. So I think this is really model and regime dependent when you have boson.
Okay.
Be a bit more careful.
Okay, thank you.